OK. All right, first things first, an announcement that you hopefully got it because I figured out how to email you all from Piazza so that it actually goes there to everybody. No labs this week. I decided it just didn't make sense to try to do labs this week or for Monday night, and then the Tuesday people, when are you going to do your lab, blah, blah, blah. So no labs this week. There's 2 more labs total. We have a lab next week, which is going to be on hashing. And then the following week is Thanksgiving. So we're not going to have labs that week. But we will have labs the first week back after Thanksgiving. That'll be the last lab. And you will also be furiously working on your final project or your final homework. So that's there. That's first thing. Second thing, if you send me an anonymous feedback and you click the button that says allow Chris to reply to you, that's great. I thought it gave you an email, but it doesn't. You have to go back online and check. So I promise you I've replied to everybody who allowed me to reply to. But you might not have gotten it, because now you think I'm a dirtbag because I didn't reply to you. But I really did. So if you did send me anonymous feedback and haven't ever seen a reply, it's not that I didn't send one. It's that you didn't go back to the website and sign in or something. I don't know why they don't send you an email. But they send me an email. They don't just send. I guess they don't send one on the way back. But anyway, just wanted to put that out. OK. So today, we're going to keep talking about hashing. I've got a quick little Unix tip of the day. But can somebody remind me what it means to hash a number? Do I need to stand you all up and move you around the room based on your birthdays or something? Can someone remind me, what does it mean to hash a number? Yeah, go ahead, Dinesh. OK, so to place it in some position, normally we make it an array. To place it in some position based on something we've done to it. Based on, what did you say? Based on an operation of that. So based on some function that we apply to it. So we might have the value 4. We apply some function, and it says go into position 4022. And then what do we normally do to that 4022? If we only have 4 spaces, how do we fit 4022 into the array? Mod. So we have a modulus operator of the number of buckets, right? Buckets. OK, so that's what we end up doing. So a hash is applying some function to a number to get another number that goes in the array in some place. Hopefully, it's a relatively random place so that we don't have these things called what? Collisions, right? And we're going to do lots of talk about how other different ways to deal with collisions than what we did earlier. OK, so that's what we're going to do mainly for today. Any questions before I get going on homework 4? No, sorry, homework 5 or anything else, labs or anything? OK, I did return homework 4 online. A few of you submitted it late, and I think once again we graded the wrong one. So I still have to do that. If you got like a 5 out of 40, and it's because you submitted it late, email me and I'll fix it. OK? All right. So first things first, the Unix tip of the day. There's this idea called piping. We've talked about this before. For this assignment, actually, you know how you have the program name, and then you do the little, I guess it's the, what is it, the less than sign to pipe the numbers into your program as if you typed them out? That's one idea of piping. There's another operator besides the less than and greater than that enables you to send output from one program into another program, into another program, into another program forever. OK, it's this idea of piping. And we're going to talk about that in a few minutes. Then we'll go into more stuff on hashing. And then finally, what we're going to talk about today is what I think is a really cool topic. It's called cryptographic hashing, which many of you guys know. Well, you should know at this point that I'm in the Navy. And by the way, somebody put on the feedback for midterm, don't hate on other services. And I feel bad about that. I did not mean to infer that I don't think other services are cool. I just like to joke about them. So anyway, so cryptographic hashing is when I was in the Navy, my original job title was cryptologist, which means we talk about things like this. So this kind of stuff is near and dear to my heart, and it's kind of cool, and I think it's neat. And by the way, none of you would ever buy anything online if it weren't for cryptography in general. It just wouldn't be possible to buy anything securely online. So we're going to get into that. OK, first things first, piping. So as I said, you can take the output of one program. Before, we've been sending the output of a program into a file or reading from a file. Now you can take the output of a program and put it into another program and keep doing that. And it's kind of an interesting idea. One of the big, what I call killer features of Unix is this idea of having tiny little programs that do one thing well and having lots of them and being able to send data or text through all those different programs. And this is what this piping allows you to do. Okay? So it's pretty neat. Let's see. What the character you use is this pipe character. It kind of looks like a pipe, right? It's the vertical bar. On my keyboard, it happens to be it's like shift \. Different keyboards have it in different places. And what you do is you take one program, put the pipe character, and then put the next program, and the output goes from one straight into the other. What's actually kind of cool is the first program can be working on some data, and then it passes some of that data to the next program. The next program starts working on the data, and the first program is working on the next data at the same exact time. So it's like multitasking individually. So it's pretty neat. OK? And that's how that actually works. Here's what I'm going to show you. If you do ls-a1, that means print just a list of all the files in your directory. OK? So for instance, if we do this here, let me move this up just a little. Nope. There we go. OK. ls-a1 lists all the folders in my, or all the files in my folder. You can't see some of them up there. But if I scroll back up, all right, I have a ton of files in here. If you scroll back up, you can't actually see them on here. It's actually hard to see. But there's two files up here. One's called dot, and one's called dot dot. Does anyone know what those ones are? Nitesh, what's dot and dot dot?
Present directory.
Yeah, period means the present directory, and two periods means the previous directory, the parent directory. If I wanted to list my files without those directories because they happen to come first in the line, I could actually use a pipe command to do that. I could say ls-al, and then let me get rid of the doc, ls-al, and then the pipe character, and then this command called tail, which says just give me the end of your like whatever the response is. If I do ls-al tail like this, it just gives me the last 10 files, or ls-a1 tail, I should say. ls-a1 through tail. Just gives me like the last 10 files. If I want to do more than the last 10, I can say, let's see, -n+3 says give me starting at the third line. So if I do that, it lists all the files, and then it does not list. Notice the first file under here is actually not the dot file anymore, because it took off the first two lines. So that's one example of piping through. OK? You can do multiple pipes. If I type ls-a1 pipe through tail -n+3, and then do another pipe through this command called wc, or word count, it will count how many words and how many lines are in the program, in whatever I outputted. So it turns out I have 221 files in my folder. Right? 221 files in that folder that it lists out for me. OK? You can keep doing this. You could, let's say I wanted to not have files that say temp in them. Let's see if I can move this over a little. Probably can't. Nope, I can't. What's that? Oh, I guess I could move the terminal over. Yeah, good point. It's kind of showing up fine on my screen, but hang on. There we go. How's that? All right. So if I wanted to list the files without temp, T-E-M-P, I could pipe this through and say this command grep -v says ignore files that match this, or ignore lines that match this, and then temp. And when I do that, no more, it doesn't say T-E-M-P anymore. But it happens now there's a T-M-P. If I want to do that, I can pipe the output through another one, grep-v T-M-P. And now it'll get rid of all the lines that have T-M-P in them. You see how it works? So you can pipe all the way through. Yeah, David?
The way that's processed, does it actually go through this every time? Because obviously that would be the most efficient way to do it if you want to look for each word each time rather than like going through the whole list.
It actually does, and when I do it this way, you can combine these two, by the way, into one command. But if you do it this way, this ls-a1 starts printing out the list of files. The first line that it gets printed out, it starts the tail function. Now the tail function has to read through it all so it knows where the end is, so that it has to wait. But it will start reading it. And then when it's done reading, it'll start putting out just the n. And then this one will start working on all that data. Everything that this puts out, this one works on. But they happen concurrently, which is kind of neat. It's one after the other, but it happens the instant that this one finishes, this one's almost about to finish because it almost got all the data. So it is pretty fast. Yeah? Secret.
Does that require extra memory usage or resource usage?
It does. Yeah, it does require extra memory. I mean, this is zero memory. I mean, this is like so few. But yeah, it's running. If you were to stop this in the middle, you would see that there's 1, 2, 3, 4 new processes that I'm running at once. They're all running right then. Yeah, which is kind of neat. Yeah, good questions. Any other? Yeah.
Say I wrote a program for homework 5 that basically checks my output
Yeah.
for 100,000 hints and checks if they're in order.
Yeah.
How would you run that through that line?
Good question. So let's say that we wanted to let's say we just wanted to do a word count or something, right? You could do this. You could do like .sort3 or sort2. You input the files that you input the like rand list 1000 or 10,000 or whatever .txt, right? And then you'd pipe it like that through word count. Okay? And that's how it would work. If we wanted to send the output to a file, remember, we just use the greater than to, my output .txt or something like that. So that's how that would work. Yeah, it's kind of fun when you start playing around. I have strung like 10 or so different commands together to get the output exactly the way I want it before. And it's better than trying to write your own program to do it. If you've already got programs that do kind of what you want, you can string them all along and do it. So, all right. Other questions on piping? OK. All right. I didn't show you this the other day. Anyone know what programming language this is in? Yeah. It's lolcat. It's actually a programming language somebody wrote that you can write in, and it will run this. I love the end thing, the k thanks bye. Right? That's like either return or exit or something like that. Yeah. So you can do this. I'm thinking about doing comp 11 in this language next time. Can you imagine? Students would riot. Yeah, anyway, so you could do this. I don't think it has all the libraries that we would need. But OK, so last time we finished up, and we started talking about this idea of collisions. I just scrunched this because I'm using a smaller screen this time. We talked about collisions. What was the name of the term that we used when we had a collision? What did we do to that collision? What did we do? I heard somebody say it. I thought, no. Chained it, right? This is a little chain. Boop, 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 right? It's a linked list that forms a chain of the next values that are all the values that go in one bucket. OK? What's nice about chaining is you don't have to do any. You can keep the same small number of buckets. What's not nice about chaining is that you have to have another data structure involved, right? Not only do we have a hash table, but now we've got these linked lists or dynamic arrays or some other data structure that's kind of, we have to stick into our hash table. And it's not particularly efficient or not particularly pretty, right? I mean, there's nothing great about chaining in that sense. But it's pretty beneficial. But there are other ways to do this. OK? So chaining, linked list. Let's see. This additional data structure is important to this. OK? And what we can do instead, take a look at this. OK? If we try to hash something to here. Now, let's say we take key 3 or whatever, and we put it here, or we try to put it here. What we would do before is we would say, OK, this one's got something in it. The key 3 is going to go in a linked list. What other options do we have? OK? What other options do we have? Where could I also put that, especially like in the array in this case? Jared? Yeah, you could put it in either here, here, or here, right? Because they're empty. Now, the fact of the matter is you need to be able to find the hash. But one way to do this is to say, OK, I think it's supposed to go here. It's supposed to go here based on the hash. But that's filled. Let's look at the next one over. That one's filled. Let's look at the next one over. Ah, that one's empty. Put it there. OK, that's another way to do this, like collision handling. OK, that's actually called linear probing, linear being 1 by 1 by 1, basically. And it works out, but we need to talk about the details of how it actually works. OK, so what you do is you take the hash code, and then you add 0 to it, because you're going to add some number to it based on how many you have to check. You're going to put it here. If it doesn't go there, you can put it there, and then you can put it. And you can try to put it in the second one, and then finally put it in the third one, like that. And then we finally put it there. OK? You keep checking neighbors until you find an empty spot, which means what? What if we had 1, 2, 3, 4, 5, 6, 7? What if we had 7 things in here, and then we tried to put an 8th in? It wouldn't work, right? So there's issues with that. You have to be very careful about how filled up your array is. We do that by what we call the load factor, which I mentioned last week. OK, but this is how this works. Just cache it to the location. If it's not there, look at the next one, look at the next one, look at the next one until you found an empty space. OK, like that. If we want to do this, and then we want to search for it, how are we going to search? Let me go back one. How are we going to search for the one that we put here? If we hash it, it thinks it's supposed to go where? Here. So it's not there. We hash it, and we look there, and it's not there. What do we do then? We keep looking. So we go to this one, and if it's not there, keep looking, and then we finally find it here. How do we know when to stop looking? What was it? I heard somebody say it. When you get to an empty space. So if you check and something's filled, you have to then go to the next and see if it's filled. And you keep going until you get to an empty space. And then you know that if it's empty space, your value is not in the table. OK? So it does take a little time to do it this way. But it actually works. And we have no more need for extra data structures. So that's kind of nice, right? You either find the key or you find the empty spot. Yeah? Good question. We'll get there in about 6 or 7 slides. You'll see. That's a very good question, though. What would happen if you emptied it? Yeah. If you take key 1 out, right, and then you look there for key 3 and it's empty, you'll say, oh, I'm done. Right? So we do have an issue. But hold off on that for a few more minutes, and we'll figure it out. OK? Good. All right. A slightly modified version of this, called quadratic probing instead of linear probing, is really simple. All it does is instead of adding 0, 1, 2, 3, it adds 0, 1, 4, 9, 16, 25. It adds the square of whatever value you're on. And what that does is it spreads things out a little bit more. If you have a number of hashes going one after the other, you're going to end up taking a lot of time if they all tend to hash to that same first location, finding the value where they all go. But if they're all like right next to each other, and you're doing this quadratic, you're going to jump a much farther distance each time. And by the way, you're going to wrap around using the modulus operator again to figure out where to put it. OK? The one thing you have to be careful here with quadratic is you can actually end up in a situation where you go and the table's not full, but you end up missing all the empty ones. And then it seems like it's full, and your algorithm never stops, and then it just hangs. And that's bad. So you have to be a little careful with that. But for the most part, the quadratic works a little bit better. OK? Question, Sam? You look like you had a question on it. Yeah?
Just like what happens if you put it in a spot, and then later when you're trying to code in a different one, it's supposed to go in that spot?
Does it? Yeah, that's a good question. So Sam says, look, OK, so I try to put it here. I try to put it here. I end up putting it here, let's say. And then another one comes along and is supposed to go here. Well, what does it do? Check, check, check. Right? I mean, these collisions do cascade to some extent. But it doesn't matter. As long as the collisions are, I mean, you know how to handle them, it doesn't really matter. OK? You do lose a little in efficiency, but it still works. Still works fine. Yeah, good question. So with the quadratic, we would try to put it in 0. Then we would try to put it in 1. Then we would try to put it in 4, and it fits. And notice we jumped over a bunch. It happens that we jumped over ones that were empty, but we jump over them. OK? All right, there are still other methods. OK? there is a method called double hashing. This says, OK, if the value where we want to hash it is full, apply another hash code and then try to put it in that location, like based on the thing, and add those two numbers together. So basically, you have the original. That one's filled. Then you have another hash code that you're going to apply. And you just multiply it by however many attempts you're making. And then that will jump it to some other place. And it will generally reduce collisions as well. OK, so it's just applying another hash function. And remember, hash functions are pretty quick. So that's good. Yeah, David.
Does that get really nasty, though, if you have all your memory is full? It's just like hashing over and over trying to find the one or two spots?
Yes, it does get really nasty. That's why you never want to leave. You want to keep your load factor relatively low, right? We'll talk about load factor in a second, but that's a key issue. You can't, because you're absolutely right. You just rehash, for a long time, and it can slow things way down. You'll figure that out in the final project, actually, if you choose a hash table. There are cases where that can happen. OK, so that's double hashing. So we've got linear probing, quadratic hashing, double hashing. OK, and yeah, double hashing would just put it in some other location. OK. And this is exactly what David's saying. He says, what happens if the table is either full or close to full? Right? You could actually fail to terminate your algorithm, because it would keep looking, keep looking, keep looking forever. That would be bad. Right? Or you could just be really slow on all of your inserts, because you're getting collision after collision. So we have to figure out what is our load factor. This is the same slide I showed you before. The load factor is just the number of keys that you've stored divided by the number of buckets you have available. And we try to keep that below some threshold. What's the threshold? A lot of times it's around 0.8, 0.7. Sometimes it can be even lower, depending on how much memory you have. Right? And you want to keep it low enough so that whatever scheme you use doesn't take too much time, doesn't have too many collisions. OK? And you have to take that into consideration. OK? Questions on that? OK. All right. Now, if the load factor gets too big, then we need to do something about it, because we need to make more space. How do we make more space in an array? Expand it. OK, here's what I want you to do. I'm going to write some stuff on the board so we can practice one of these. I want you to talk to amongst yourselves and figure out how we're going to expand our hash table. What do we have to do to expand it? And is it easy? Is it hard? Is there something we have to consider? Think about that for like 5 minutes while I'm writing this other stuff on the board. OK, go. OK, have you gotten some time to think about it? All right, before you give me the answer, let's practice hashing some things. And what I've done is I've come up with a couple pairs. Here's the key. Here's the value. OK? And I've just said some function, and I'm not telling you what that function is because it doesn't actually matter, will hash 10 to 9, 20 to 6, 30 to 12, 40 to 1, before we do any modding to it. OK, so that's the original hash function. We haven't modded anything yet. OK, so if I have a hash table of 4 values, OK, where is this one going to go? It's supposed to go in location 9. OK, so what do we do to that 9 to fit it in our table? Mod 4. 9 mod 4 means 9 divided by 9 goes into 4 how many times? What's that? Not careful. Not sorry, did I say that wrong? Yeah, sorry. 4 goes into 9 how many times? No, wait a minute. No, it's the other way around. 9 mod 4, right? Oh, no, you're right. 4 goes into 9. Sorry. I'm a moron. OK, 4 goes into 9 how many times? 2. So how much is the remainder? 1. OK, so it's going to go right here, right? So what do we have to put there? We have to put 10, and we have to put A, because the whole point is we're storing the data there, right? Yeah, so you don't want to have like extra places. You're going to store both. But you're going to store both because we might need to look for it later. OK, where's the 6 going to go? 6 mod 4 is 2. So we're going to put, oops, sorry, we're going to put 20 and B here. And then 30 goes to 12. 12 mod 4 is what? 0. And so that's going to be 30 and C. And then 40 and D is going to try to go where? 1 mod 4. 1 mod 4 is 1, right? So it's going to try to go there. Doesn't go there because there's already somebody there. Linear probing means it's going to try to go there. And it's no somebody's there. So it's going to finally land here. And we're going to have 40 and D. OK, everybody see how that worked? That's a pretty standard like hash table. Now, what's our load factor? It's 1, right? Because the number of elements is 4, and the amount of space is 4. So we can't add anything else to here. No matter what else I put, we can't add anything else. It's just no way to do it. OK, so we're going to expand it. So I've created a new array that's double the size. How do you guys think we're going to expand it? What are some ideas that you had? Oh, by the way, before we even get that, let's just search. If we search for 10, we look in spot 1, right? There it is. If we search for the other ones, if we search for 40, we look in spot 1 as well. Not there, but it's not empty. Not there, but it's not empty. There it is right there. So you see how searching works? OK. All right, sorry. Who was going to say? Somebody had their hand up about it. Dinesh, you've answered a couple times already. Let's get somebody on that side of the room. Somebody over there, up on that side of the room, who thinks they have an idea. And then I'll give you a chance. What's a good way to get the data into the other part of into the new array? Because we're expanding it, right? What did you guys talk about for 5 minutes? This weekend? I was in Seattle all weekend. I got back at 6 a.m. I'm tired. What do you guys think? Just throw out some ideas. No pressure here. What do you guys think over in that corner? I'm going to start picking on somebody. If you don't actually raise your hand. And Bika, what do you think? You could rehash. OK, I like that, actually. OK, I like that. So before we get to that solution, did anybody say, look, let's try to spread these out somehow over here? Or just copy them? I mean, the problem with copying them is what? If I just made 30C, 10A, 20B, 40D, if I did that, what's the problem with that? Yeah, go ahead, Mackenzie. Yeah, let's look at a good example. Let's see. Hopefully I picked one that would actually work right. The 6, right?
Yeah, that would go in mod.
That would now be not mod 4 anymore, but it would be mod 8. So it would try to go in what spot? Spot 6. So when we go to look for it again, we would go here. Oh, it's not there. 40 is not in our table. So we would lose the hash. So you can't just copy it over. OK, so that's one issue. All right. If you try to do any other scheme where you're just trying to manipulate that data somehow in here without rehashing, then you're going to be in trouble, right? OK, so Ambika, you say rehash. What do you mean by that?
So you take like everything that's in here right now and hash it based on the
based on the new array, exactly. So 30, we said, goes to 12. Now we're going to do 12 mod 8, right? And 12 mod 8 is what? 4. So this one's going to be 30, and C goes there. All right, and then we go to the next one, and it's 10, which was 9. 9 mod 8 is what? 1. So that's going to go right here. Turns out it's in the same place. OK, and then 20 was 6 mod 8. We already said was 6. So that's going to be over here, 20 and B. And then the 40 we said was 1. 1 mod 8 is what? 1. And it actually would try to go there. So where does it really go? Here, 40 and D. We've rehashed this. What's the issue with rehashing, though? Takes time, right? That's the big issue with rehashing. It does take a little time. Now, hopefully your hash function is fast. That's the point. We try to make fast hash functions. But you do have to go through and rehash them. You can't just copy them. OK, so that's the issue with that. But now we have a new hash table. And we can now find all our hashes because they are hashed to the proper size of the table. And we've got more space. And now we can start adding other keys to that hash table. OK? You will be expected. You'll probably have to do this on your final project. If you pick a hash table for your data structure, you will have to expand it. So I will give you some hints about a good way to do that. But pay attention to this stuff and look online to see how it's done. So this is exactly what we just went through. Rehash all the keys. You can do this other thing called consistent hashing, which you have to figure out the hashing function so that most of the keys don't change. But it's not easy to do. And I'm not going to expect you to know that, or I don't even know how to do it. So you can look it up probably and figure out. But it's not something that's simple to do. Yeah, Danielle.
Do you want to expand for the arrays too?
What do you think? You absolutely want to expand before. When you calculate, every time you insert, calculate your new load factor. And when your load factor gets above some value that you choose, like 0.7, rehash everybody. Yeah, so you definitely don't want to wait too long for 2 reasons. First of all, you'll just be really slow in here, right? And then, well, I guess that's really the big reason. I mean, I was going to say the other reason is that rehashing takes longer. But it's going to take the same amount of time. It's just a matter of you want to do it when you're still guaranteed that it's going to be pretty fast access. Yeah. OK. Good. Yeah. Isabel.
What number that you're just saying, but you always have to mod it by the size of the array.
You do have to mod it by the size of the array. That's kind of how it fits in the array. Yeah. Otherwise, you wouldn't necessarily you would miss out on some values. But you definitely want to mod it by the size of the array. Yeah. OK. All right. Good. That's the how we do expansion in a hash table. OK. Now, this is back to what Dinesh was saying. What if we delete one of the values? So let's say that we went over here and we deleted. Well, we've got our example up here. If we came in and we said delete 10, right? If we want to look for 40, we're going to look here because, sorry, was that right? Did I do the wrong one? No, that's right. We were going to look, right, we're going to look here, and it's empty, so we're going to stop, and we're going to say that 40 isn't in the table. Not going to work out. We can't just delete it and say everything's going to work out. So what could we do if we do that? What are some options to us here? Sure, what do you think?
Like, could we put a shop item in there that's like, hey, there's going to be stuff after this I'm not really empty?
Yeah. Yeah, why don't we just mark this as being deleted? Right? So you can mark it as being deleted. And then if you get to it, it's empty. So you could put something there. But if you're trying to search, you just say, oh, it's not empty, really. There's other stuff I have to search for. Yeah, so that's exactly what you do. That's one solution. So good job. Right? All right, there you go. You guys ever been in class where like professors throw out candy? Ever been in that? I always think that's a bit hokey. But anyway. Supposedly somebody tried to do that when they applied here, and the students were like, no. I mean, it's good if you get a piece, but throw it back in. OK, so there's the case where you never find it, right? And what you can do is you can just say, look, there's a deleted one there. Now, how do we deal with that deleted spot? like that deleted spot is really causing us a little bit of heartache, right? Because we've got, like we now have to search for 2 and 3 by first going here when that spot is really where both 2 and 3 need to go. So what could we do to mitigate that? How do we make it so that it does that? What do you think? We could put one of them back. Now, if we put 2 there, what would we have to put here? Well, yeah, we could move all of them. Or we would have to put deleted. So that's not a bad idea. There's 2 other solutions. What do you think, Erica?
We could just move key 3 into the deleted spot.
Yeah, so how would you find key 3?
And just keep going with the linear search or whichever search method you're using until it's either empty or doesn't apply to that key.
Doesn't apply to the key is tough. Empty is also tough, because what if something else went in there? And then you wouldn't know if it was empty. So that's a little tricky. Like, to find the last one is tricky. If you had a way of finding the last one, and there might be other values there might be other ways to find the last one, like marking it as the last one in the search and every time, and that sort of thing. So, but there is. But you would definitely you could just move 3 over there. That would work. Yeah. Could you store which as a temp? How would you know key 3 existed, though? Like, how would you know? So let's say you hash something here, and then you hash this, and you hash this. And then you delete key 1. How do you know key 3 is also part of, should be here? That's the only problem. But what you can do instead, this is actually kind of clever. The next time you need to find one, just move it then. Because you know it exists. It's the one you're looking for. Move it back to the deleted spot there. So keep a list of like the first deleted spot. When you find the one you're looking for, say, oh, guess what? I'll take a time right now and move it over there. That works too. OK? That works too. OK? So if we know this deleted, we look, and then there it is. OK? And then we can now move key 3 back over to the key where the place that we deleted. And there you go. OK? Questions on that? That's not too bad, hopefully. So yeah.
So just to be clear, you have to make sure that there were no other values after key 3. That's
well, what you would probably do is put this one as deleted, right? It just means that it's just going to make you have to search fewer times later for that value, right? Yeah. You're getting to it's going to be hard to empty one again, because you really don't know where you got to go to figure out if it's empty. Yeah. I mean, I think if there were 2 empties in a row, you could probably do it, but it's a little tricky. Yeah, maybe if you get the last one. I'm not sure it's worth doing the extra coding to do that, but you might. Yeah, you could probably do that. Isabella?
So if you keep moving the movement around keys to fit,
Yeah.
responsible, all the values for the keys end up being the fixes that they weren't originally had.
Sure. Yeah, and that slows down your hash table. But can you still find them? Yeah, you could still find them. You always go to the one that you're looking for. Like you go to the original hash, and you say, hey, are you there? And then if it's not, you just start walking the list until you find it, or jumping the list, or whatever.
What if it's like behind where you're looking for? Like if you back, what is it?
Oh, because it's circular?
Oh, okay.
I mean, it's circular, remember, so you would eventually jump around. But yeah, you do have to, and again, that would mean that if you were at the end, like if you were at the last one, it could wrap around to the first one. Yeah. And you always do the modulus operator on it to find it. Yeah, Anna?
So after we move key 3, we make where it went to store a deleted.
We would make that one deleted, yeah.
What if we like search for something that was where key 3 was,
Mm-hmm.
and then it sees deleted and starts searching, even though it was actually empty?
It would search. You would have to search there. Yeah, nothing you can really do about it. Yeah. I suppose. Well, what you could do. Let's say another strategy is. So after you get 100 deletes, rehash everybody. You know what I mean? Like just go through and clean everything up. Like do a whole complete rehash. You could make, depending on how well it's working or not, you could do that. Yeah. So lots of different strategies, though. Okay. All right. So that was the end of the hashing that I expect you to be able to do, right? You're going to have to be able to take a hash function and apply it to an actual hash like we did up here. You're going to have to be able to talk about how to expand. The next stuff we're going to go on is stuff that you need to know but not know how to do. OK, so a little bit different there. Just a couple things on that. And what I've got is a bunch of little links. If you get interested in this, there's other links you can go to find like more information about this stuff. Is there a perfect hash function? In other words, a hash function that for your array will never have any collisions. What did we talk about with the birthday problem? Even with like random things, you can't get a perfect hash function unless, as it turns out, if you know all the keys ahead of time. Okay, if you already know the keys, you can construct a hash that will be able to make it so that every time you get a new key, it goes into the, or you can construct the table so that your hashes are do not have any collisions. That's kind of nice. That guarantees you O1 complexity. Great. Hard to do, though. Okay? It's hard to do except in trivial cases. The one that the 2 character words we used from last week, not too bad to do that. We did that. That's not only a perfect hash, that's what we call a perfect minimal hash, which I'll get to on the next slide. But that means that we can have an array that's this big, and we know exactly all the elements are filled in it because we have every 2-letter word that we know, for instance. Okay? There's some papers in here you can read about it that talk about how to figure out perfect hashes. Yeah? Well, with a perfect hash function, you won't get 2 keys that are the same. That's the point of a perfect hash function. Sorry, 2 keys that are the same. Sorry. Yeah, I guess you probably aren't allowed to do that with a perfect hash function. You're either going to have to somehow represent those in one bucket, or do some sort of collision, because it is a collision if it's the same value. So yeah, with a perfect one, you wouldn't want duplicate keys. Okay? Or remember, and as I said, like the Python language, when you put something into a table that's already there, if the key is already there, it replaces it with what you're putting in there now. So there's no, the collision is, if it's a direct collision with the same key, it just replaces it. So another option. OK. Perfect hash function, if it has exactly n buckets for n keys, is called a minimal perfect hash. That's the 2-letter word example we used the other day. More papers on that if you want to read more about that. Okay. All right. So this next part, as I was talking, this is kind of neat. Okay? Cryptographic hashing. All right. What we're talking about here is taking some phrase and applying a hash to it like this nice long word here. Okay? It's actually a number, I should say. And it's a hexadecimal number because it's got B's and F's and E's. It goes all the way up to F. Base 16 number. Coming up with a phrase or a word that turns into this number, okay, such that you can't go backwards and figure out where it came from. Okay? That's what we're talking about here. Anyone happen to know what this stands for? This number? Any guesses? Struggle bus. Right? There's a struggle bus down there. I learned this word last year, and some students were like, it's a struggle bus. Anyway. And by the way, a struggle bus is what it would take for you to go backwards from this to struggle bus. Right? That's kind of the point of this. You can't go from this number and get back to struggle bus. Okay? It's what we call a one-way function, which mathematically speaking is really weird, thinking, oh, I can't go backwards from a function. You think mathematically you can do the inverse function, but there's lots of functions you can't do that. For instance, if I say x mod 22 equals 7, what was x? What could it have been? Anything that yields 7 from modding 22, but it could be an infinite number of things, right? So that's one idea of a one-way function. It's not a very good one, because you can limit it to what it could be. But that's one idea of it. So these are the kinds of things that we're going to talk about over the next few slides. OK? All right. So here's what a cryptographic hash function is. It's a hash function that takes an arbitrary block of data. In other words, it doesn't matter how long it is. It could be 2 characters, could be 1,000 characters. And it turns it into a fixed length string, like this one, right, such that any change to the data will change the hash value. That part is neat, too. If you change struggle bus to anything else, you will get a very different number out of it. We call this the digest or the hash that comes out of it. If you want to do this on your own, if you want to like hash things, there's a Python command you can use. This is really small text, I know. But look on the slides. You can actually import it. There's this library called hashlib, which you can import, and it will give you this number from strugglebus. Okay? So you can come up with this from a cryptographic hash. Okay? Well, if we're talking about cryptographic hashes, there's actually 4 properties which are really important. Okay, kind of the main properties about this. All right. The first property, we will go through each one of these individually. But the first property is it's easy to compute the hash value. In other words, we're not trying to make like really long, detailed like functions here. We want it to be relatively fast. Not always. We'll talk about that later. But we want it to be fast so that it's easy to compute the result. We don't want to have to go through all sorts of weird function things. Just easy to compute and done. You want it to be infeasible to generate a message that has a particular hash. In other words, if I give you that long number, if I give you this long number, you shouldn't be able to find a message that makes that hash. You shouldn't be able to find strugglebus, okay, or any other message that happens to make that hash. It should be really hard for you to do that. Okay? All right? It should be infeasible to modify a message without changing the hash. This is an interesting part too. Okay? I'll show you an example of that too. This means that if you change something about it, the whole hash will change. Okay? It's infeasible to find 2 different messages with the same hash. So let's say you know strugglebus maps to that big long number, right? Strugglebus maps to this long number. It should be really hard to find something else that also matches to this, even if you know strugglebus goes to this one. Okay? So those are the big 4 things. We'll talk about those in detail. Okay? The first one's easy. It's easy to compute the hash. If you need to compute a lot of hashes, you want it to be pretty fast. Okay? You don't want to have to chug along. Now, again, there are times when maybe we don't want that. But in general, cryptographic hashing, we want them to be relatively fast to do this. It should also be very fast to verify whether or not a hash came from a particular message. So if you've got a hash and you've got strugglebus and you want to see if they line up, if they are indeed the correct pair, it should be fast to do that. Okay? All right. The second one, it should be infeasible to generate a message that has a given hash. Now this is where, like, think passwords. Okay? So let's say my password is hello, because I'm not very bright. Right? My password is hello. And then Ethan comes along, and he has a password that's hello1, because he's a little brighter than me. Right? It should not be true that his password should create a completely different hash. That's actually kind of the next thing. But if my password is hello and has a certain hash, it should be really hard for somebody else's password to also go to that hash. Because you don't want 2 people's passwords to create the same hash. Okay? We talked about this one way. We don't want to be able to go backwards from hash to the message. Okay? And we also don't want somebody, and we will get into this deception thing a little bit later, but you don't want somebody to be able to trick you and say, I created this hash from this message, right? And it turns out it was some other message that created it. Okay, that would be really bad if you're trying to like pass secrets around. Okay? Questions on this so far? Okay. Yeah?
So 2 people have the same password, though?
If 2 people have the same password and all you're doing is hashing them, yes, they will have the same hash. We'll talk about strategies to mitigate that in a few minutes as well. Okay, we'll talk about that in a few minutes. OK, this is the one that I was talking about where it should be infeasible to modify a message without changing the hash. So my password is strugglebus, right? And this is my hash, 05B528EF, etc. Right? Cecily comes along and says, no, my password is strugglebub, right? And strugglebub goes to 4BFF5E. Notice these 2 numbers are like completely different. They might share a few characters everywhere, but that's just going to be random. Completely different for one change in character. Okay? And that's good, because let's say that somebody steals my password and steals the hash file of all the password hashes. If my password is strugglebus and they know that it goes to this, if the hashes were similar, then strugglebub might go to something similar. And so then they would see that like Cecily and my hashes are similar. They might be able to guess her password. If it's a completely different number, they'll have no way of guessing her password. Yeah, Danielle. Yeah, if you put struggle bus without a space, it would be a completely different hash as well. Yeah, every character counts, even the spaces. Yep, yep, they all count. Yeah, Josh.
So is there a particular reason why I always need to put in a capital letter and a number? Is that just the value that they have makes it change up more?
That is a different thing altogether, but that goes to actually something we'll talk about in a few minutes. That goes to the fact that you want the number of different passwords to be huge. Right? So if you just pick 26 characters, like if you just said anybody, you can use a lowercase letter. You pick a dictionary and just do all the lowercase letters, you'll start picking your passwords out pretty quickly, right? So that's the reason they make all these strange rules. Now, they shouldn't make all those strange rules. There's much better ways of doing it, because now some people like write their passwords down, right? In the Navy, it's terrible. I probably literally have 8 to 10 different passwords for various systems I have to log into. I don't remember all those passwords. And some make me change every 30 days, and some make me change every 60 days, and some's 45. And then I have to memorize it, and they make me do an uppercase and a lowercase and 2 special characters, and you can't duplicate characters, and I never remember. And so then I like write a hint to myself, and that's just bad. You know, you shouldn't be writing those things down. So yeah, Mac.
Are you allowed to use something like keypads?
No, I'm not allowed to use anything. I'm allowed to use my brain, and my brain's not that fast. Like, and not that smart to figure out these things. It's just hard to remember that many different passes. But no, you can't in those things. It's all it's not. Most of them aren't even connected to any internet or anything either. So, and you can't install programs on them. So, you know, I mean, I can't bring anything electronic in with me. So no, it's kind of ridiculous. But yeah, but that's the idea. You want to be able to make lots of different types of passwords. There's a great XKCD comic about that if you want to look it up. Yeah. What is the password? Direct horse battery. Oh, what? Correct horse battery staple. That's the password. If you use a password that has 4 different words in it that are random words, you can memorize it pretty easily by like some mnemonics, but nobody will ever guess it. And not even a computer, because it's like huge sample space. OK, let's keep going on this. So the final one is it's infeasible to find 2 different messages with the same hash. That goes back to the password thing. If my password hashes something, you don't want somebody else's password to give you the same hash, even if it's the same password, but that's a different story. But so you don't want 2 passwords to collide. OK, so collision avoidance is what you need to strive for. It's hard. There will be some collisions, but you try to avoid them. OK, if you do it right, you can make it so that collisions, like to get a collision, would take until the heat death of the universe to figure out. If you do it right. OK. So let's go into some examples here. Now, you guys all recognize Alice from Alice in Wonderland, right? And then this is Bob from Sideshow Bob from The Simpsons. In this case, these 2 are good guys. Normally, the way cryptographers do this is they normally talk about Alice and Bob being good guys. And then they talk about this person, Eve, who's like eavesdropping, right? And Eve's the bad guy. But in this case, and Bob will eventually become the bad guy here. But for now, Alice and Bob are both good guys. Here's an example of when you might want to use a cryptographic hash. Let's say that Alice has this math problem she's working on. OK? It's a little hokey example. But say she has this math problem she's working on, and she solves it. And then she tells Bob, hey, I just solved that math problem. And Bob says, I'm not sure if you solved it or not. I'm going to go solve it. And Alice says, let me hash my solution and give you the hash. And then now you can start working on the problem. And later, when you solve the problem, I will give you my original solution, and you can hash it and see that it is the hash that I gave you. And therefore, you know that I came up with the solution before. But Bob couldn't figure it out. OK? Does that make sense? Let me restate it. Alice has this problem she's working on. OK? And she figures it out. And then she applies a hash to it and gets a really long number. And her solution is now hashed into that long number. She can give that long number to Bob. Does he have any idea what the solution is? No, he just sees this long number, right? But he knows when she gave it to him. And he then solves it and says, OK, this is the solution. Then if she gives him the original message and tells him how she hashed it, he can then hash her solution, come up with that hash value, and say, oh, yeah, you did solve it back 10 days ago when you gave it to me. See how that works? It's like a way of proving that you do something without giving away the answer. You can do that. So that's what happens here. And that's one way to use these cryptographic hashes. OK, kind of neat. You can also have what we call password verification. OK. When you go to a website, actually, let's use an example of the school here. When you go onto the homework server and you type your password in, OK, what it's doing is it's going and figuring out that you're the person that typed the password in, like it's actually you, by comparing hashes here. What it does is it takes your password and it hashes it. And then it doesn't store your password anywhere. In fact, if you forget your password, anybody forget their password so far this year and have to reset it? You can actually reset it online. But if you wanted to call up the system administrators, maybe you liked that password and you think, I really like that password. I want to get it back even though I don't remember it quite exactly. You call up the system administrators and say, hey, could you guys tell me my password? What's their answer going to be? It's going to be no. And it's not going to be no because they don't like you or they don't want to tell you over the phone. It's going to be no because they have no idea what your password is. And they never have and they never will. Because what they do is they just compare hashes. All they do is keep your hash. And then when you try to log on again, what does the computer do? Hashes your password and then compares the hash to what it has on the computer. So nobody ever has your password again. OK, so that's kind of clever. It's a clever way of doing it, right? So it doesn't reveal the passwords automatically. OK? And you mask that. Now, sometimes you go to a website. One sec, Dinesh. Sometimes you go to a website and you forget your password, and then they email you your password. Right? Nah, it makes me rip my hair out when they email me my password. Because number one, they just sent my password over clear like the internet, right, with all the communists in there, right? And then they were trying to steal my password. And then they actually have it somewhere. Like it might be encrypted on their side, but it's not encrypted when they send it to me. So bad news. Dinesh, you had a question. Ah, good question. How do these millions how do these credit cards get stolen and all that? Well, there's lots of different ways they do that. What people, a lot of times they keep them either unencrypted or encrypted in a way that can be decrypted. Or people can steal the hashes. And then on the next slide, I think it tells you how they do it. You can actually break these using certain tools that I'll show you how to do. But yeah, it's mind-boggling how this happens. But it's because people have poor security in their websites, really. Yeah. Did you have another comment, Max? Or do you? They have to be what?
Like they have to be.
Oh, you have to get the credit card. Oh, you do. I guess you do have to keep the credit card numbers in order to pass it on to the bank or whatever. So yeah, it's not just an authentication. It's you have to actually use it. So that's probably the other one there. But well, yeah, we'll get to your comment in a second. And this kind of goes back. This is the question I asked at the end of the other day, right? Is there a case where hashing should be slow? OK. Max immediately raised his hand. I told him not to tell anybody. Can anybody else think about when you might want passwords hashing, or I gave it away, hashing to be slow? Passwords. Oh, good. Why? Why would you want your password hashing to be slow? Max, why do you think?
Because then when you rainbow table it, it's going to be harder to.
OK, explain. You said rainbow table. What does that mean?
There's a certain method of breaking hashes where you literally try every combination possible to see if the hash is right.
Yeah.
That's a lot harder when you're hashing algorithms really slow.
Yeah, if you have the ability to create a bunch of hashes based on various words or phrases or whatever, and you can do that really fast, you can come up with lots of hashes, which you can then compare to hashes that you might have stolen, which is easier to do than you'd think. And you could do that. So that's a good point. What was your comment back? What did you have back there?
I was going to say, if it was slower, then they would be able to brute force.
Yep, it's all about brute forcing. Brute forcing is meaning you can try millions and millions of combinations at a time. Josh, did you have something? Same thing, yeah. Yeah, so this is when you want it to be that. Yeah, Max.
There's also a timing impact.
There's a what?
You can see how fast the password is.
Oh, yeah. You also, right. There's also various interesting attacks where if you type in a password, if someone types in their password, you can kind of figure out what the password was by how long it takes to hash it. So what you want to do is you want to do fake hashing parts of it. You want to make them all take the same amount of time to hash. If your password's 5 characters or 50, you want to take about the same amount of time to hash. Because trust me, the NSA thinks about this stuff all the time. right, about how to do this. So do the communists. But so let's say that Bob is now a bad guy, and he steals a bunch of usernames and hashes. If he has the ability to create lots of hashes fast, and by the way, most hash functions are public. You know exactly how to hash. In fact, if you want to know how to hash onto the homework server, you can look it up. Look up Red Hat 6 password hashing function, and you will be able to find exactly the function that gives you your password hash. Right? Why is that a good thing? Why would it be a good thing? Why would it be a good thing to be able to know how to hash everybody's functions? What do you think?
Because I mean, theoretically, if they're really good hash functions, then you shouldn't be able to like backtrace them, and then it gives everybody the opportunity to have like pretty ironclad security.
There you go. Well, it gives people the ability to have good security, and also what else? There's always someone smarter than you. Yeah, it gives people a chance to test it, right? If I give you a black box and said put your password in here and out popped a hash, but I said I'm not going to tell you what I'm doing inside, I could have a really weak function that you have no idea how to test. But if I say I'm using the Linux Red Hat 5 public function, you can go and look at it and test it and figure out that it's secure, and lots of people will do that. So that's very good. But what Bob can do is he can create all these hashes, and if it takes a long time to create them, then it slows them down, which is good. But if you can do it fast, and these days, guess what? With GPUs and with other like fast parallel processing, you can still do a lot of these fast. Even though 5 years ago a password hash function might have been slow, now it's fast because you've got so much more computing power. OK? Yeah, Isabel. So instead of taking a millisecond to create your password, it might take a whole second, right? Which doesn't seem like long, but if you're trying to create 1 billion passwords, you're never going to get done with that if it takes a second to do it, right? So the difference between like a microsecond and a second, right? I mean, 1 million times slower is that's what we're talking about. Yeah?
Also for regular tables, all the combinations are generally made available in databases online.
Oh yeah, you can. So if you went back and looked up that number that I put for struggle bus, it might actually give you struggle bus, right? Or if you, so it's, there's lots of combinations that are actually published online because people like to publish those sorts of things. Anyway, so that's what you can do. There's this idea that Max has already brought up called a rainbow table, which says here's the list of all the hashes based on a whole bunch of different random words. And what kinds of words do they normally choose to try out passwords? Password, Fido, right? I love my dog, whatever. They try all these different things that like people come up with for passwords, right? Go Jumbos, right? They're going to try that, right? Why? Because it's probably a password somebody at Tufts is using, right? No? I bet somebody at Tufts uses Go Jumbos. But anyway, so you want to be able to do that. Now, this is called key stretching. Just means take more time to create your key. OK? So another interesting, so with the increasing computing power, you still got, even with key stretching, it takes a long time to do this. People have changed methods slightly, where instead of taking a lot of computing power to create your hashes, it actually takes a lot of memory to create your hashes. OK, so it's harder to do a lot of hashes at once if you run out of memory, if you're trying to do them all in parallel or something. So there's other ways of stretching the time out, basing it not on computing power, even though computing power is really fast these days. A final solution is the following. And Ethan brought it up earlier. If I have my password as Fido, right? OK, and Graham has his password as Fido, aren't we going to have the same hash in the values that are hashed for our passwords? And so if someone knows my password, Fido, and they can look at my hash and compare it to Graham's hash, which is also Fido, then all of a sudden they're going to be able to know his password too. So far, so good? What we do about that is really clever. We say, fine, my password is Chris Fido, and Graham's password is Graham Fido, or whatever his username is, or some other information that can be perfectly public, but it's different for both of us. So every one of us in here has what we call an individual salt, kind of like salting I don't know exactly the analogy they use, but the idea is you do this thing called a salt based on like your username, which takes your username, adds it to the password, and then Graham and I now have different passwords, even though we really think we really have the same password. But under the covers, we have two different passwords. Mine's Chris Fido, and his is Graham Fido. See the difference? That's called password salting. And what it does is it makes it so that you have to do many, many, many rainbow tables instead of just one, because you need a rainbow table for every different username, which would take forever. So it's actually a really good way of doing this. OK? All right, questions on that stuff? Yes?
But even if you guys have like different username,
Yeah.
the last half would exactly the same.
The latter half would be the same, but remember when we hash something that's different, it makes a completely different hash. Remember how we did struggle bus and struggle bub? And those were two totally different numbers? Right? When Graham types in his password, he types Fido. And then what it does is it doesn't just hash Fido. It hashes Graham Fido. It goes Graham Fido. And that hash is going to be way different than my hash, which is Chris Fido. Even though we have the same password, the salt is different, so it makes a completely different number. Yeah. So it's interesting that way. OK, let's see. So here's another example. And you could go and test this or you can go check this out if you want. When you're downloading stuff from the internet, OK, how do you know that you're getting what you think you're getting? Right? You may not know. If you download Firefox from some random website, right? It could be Firefox that has some Trojan horse in it that's going to go and let somebody else log into your computer. OK? It could be. But what you can do is you can download Firefox. Then you can go to the Firefox website. And you can find what they call the checksum, which is just the hash on the whole file. OK? And it's a number. And it's just like the numbers we saw before. And you can then, when you downloaded the file, run that file through a little program, in this case called MD5, which is a type of hash. Run the program through MD5, and it will tell you that number that Linux says that their binary file is for. And if they do that, if the numbers match up, you know you got the one that Mozilla, the Firefox people, gave you. OK? So it's not a bad way to check and verify that you've got the right file. And there's no easy way to come up with another file that creates the same hash. Therefore, you know you've got the right one. Yeah?
What if Mozilla's been compromised, then they could also have fake?
Yeah, if Mozilla's been compromised, they would have fake checksums, yes. But hopefully they're checking and making sure they aren't. Yeah, I mean, it's not 100% foolproof, but it is definitely it's definitely one way to do it. Or if you like torrent big things like Linux distributions or whatever, you can check the checksum at the end and see if it's the right one, and then you know if you got any like missing pieces of the file or whatever. Yeah, David.
Would it be the case that as the size of your file increases relative to the size of your hash, I know that won't actually make it feasible to decode the result, but you would still have a larger number of files that would actually correlate to that hash, and that could get like extremely, that could get like billions, trillions.
Yeah, you could. You could. That's why you try to use a big enough hash. But you're right. You're absolutely right. The bigger the file, the more likely it's going to be. But still pretty unlikely. Right? But you're right. And there have been attacks against these systems. Like MD5 is not a good example, because that's kind of been shown to be relatively weak these days. But it's the example I used here. OK. All right. So how do you know that an email came from the person who says they sent it to you? You get an email. Not like from a Nigerian prince or something, right? But you get an email from like like you get an email from your buddy, and it says, "Hey, did you hear about such and such?" And you want to go, "Hey, maybe somebody else is sent that email to me." There's a way to do that, OK, using this idea called public and private keys, and it is the coolest thing. And in fact, you would never buy anything off Amazon if it weren't for public and private keys. In fact, Amazon.com wouldn't even exist if it weren't for public and private keys, which basically says, hey, I know who you, like I can trust that you are who you are by looking at your, looking at your public version of your key. Well, it's not really that easy. It's basically, I can give you my public key, and you can send me something, and I know it came from you. That's basically the way it is. OK? And did I say that right? No, I said that wrong. But you can't generate the public key without the private. Well, here's what it is. You've got two keys. You've got a public key and a private key, and they're linked together through one of these one-way functions. Okay? The public key allows people to encrypt something that only you can decrypt. Right? The private key allows you to decrypt like anything that was encrypted with your public key. So that's how it kind of works. But what's cool is you can actually, if you want to send me an email, I guess I did say it right the first time. If you want to send me an email, you can take that email and let's see, you can encrypt it with your private key, and I can decrypt it with your public key. And only your public key will decrypt it. And therefore, I know it came from you. Right? And so that's how you can do these things. So it works great with this, like that sort of thing. It also works great to like pass credit card numbers back and forth. And it works great to do computer-to-computer interactions, these whole like public and private key things. Okay, so it's pretty cool how it actually works. Okay, this is what I just said. Alice has a private key, and she also has a public key. Anyone can get it. Okay, you can find out what people trade them back and forth if you want, or computers do. And then she hashes her message to Bob using her private key, and Bob can read it, and he takes her public key and gets the answer out of it. Okay, gets her original, and he knows it had to be sent from her. Okay, so it's pretty cool, pretty neat stuff. Okay? Web security, all based on that. Okay. All right, lots of references here. So questions on any public, private key, any cryptographic hashing, all that stuff? I will not make you know a lot of that. Just kind of have it in your brain. I won't make you do any of it, obviously. But what's that? Yeah?
So back on the topic of how people will post the hashes online.
Yeah.
So are they posting the actual like way they hash it? Like,
Yeah. They would say, I used an MD5 hash to do this.
so then wouldn't somebody who's trying to break a hash just like scour the internet for these different things to try and just plug them all into something?
Yeah, the thing is, if you use a good hash function, it's going to be hard to do that. It would take you years to do that on regular old computers. Now, the NSA can do it pretty quickly, probably. But you know, you and I can't really do that easily.
Yeah, that's true.
Yeah. Good. Other questions? OK. I'll see you guys later. No labs this week, remember. And homework's due Friday night.